Alright, hell yeah. So we have a derivative, and man, what the hell is this? This is cosecant. Okay, so hell yeah. So we're going to do this one. And this ain't my first rodeo, but I have not done this problem. So I don't know if I'm totally going to strike out. But here is what I've learned from doing, I have looked up inverse tangent of x, the derivative of that with respect to x. And I have done for myself sine, inverse sine. Okay, so the first strategy that I'm going to do is inverse of something. So in here, this is going to be a ratio. And then the derivative of this is going to give us an angle. So that's kind of the first thing that we need to go over, is that if I have inverse sine of something in here, this is going to generate an angle. So I sometimes just spell out the word ratio. And I guess using x is cool, you know what I mean? It's all right. I would rather see this than, I wouldn't use sine x. Knowing that this is an angle. I know you probably just have to use it, doing complex integrations and stuff. But it's just nice to kind of separate. That's the first thing. When you're dealing with triangles, like, hey, is this an angle or is it a ratio? It can only be two things. The second thing that I think is a prerequisite for this problem is for sure knowing what a basic right triangle is. You have an angle. We're going to say this hypotenuse is 1. And now if this is the angle, make some sun rays. Sun is shining on the sinus. So this component is 1 sine theta or just sine theta. When your hypotenuse is 1, the sine component is the percentage of the hypotenuse. But in this case, this number will be between 0 and 1. Like if it's 0.5 with a 30-degree triangle, that means it's 50% of this value of 1, whatever units that is. All right, and the adjacent is cosine. And sweet. So now we can kind of run through all the others. Like all tangent of this angle means is just the ratio of this side to this side. It doesn't matter if it has the hypotenuse in it. If the hypotenuse is 10, this could be 10 sine theta divided by cosine. But you're just going to have the sine component divided by the cosine component. Now, even like right now, it's like the one thing you can always forget. I always forget when dealing with right triangles, and especially when trying to dive into the angles and sines and cosines and tangents to explain the right triangle. I always forget about Pythagorean's theorem. I mean, we have a right triangle. That means that this side squared plus this side squared equals that side squared. And so that's where that identity comes from. So we're going to have sine squared theta plus cosine squared theta is equal to 1 squared is just 1. All right, hell yeah. And it's from this identity that you have to manipulate this identity to get other identities. And so like one common thing to do is just, hey, let's just divide everything by sine squared theta. And then when we do that, let's see what we have. This is 1, and then this is cosine squared divided by sine squared. That's the same thing as cosine theta, sine theta, and then just the same thing twice. And if I know sine theta divided by cosine theta is tangent, the opposite of this, cosine theta divided by sine theta, is cotangent of the angle. Sweet. So right here, this is just going to be cotangent times cotangent, or what we would say is cotangent squared of the angle. And then this is 1 divided by sine squared theta. Sine squared is cosecant. So we would have cosecant squared theta. All right, so hell yeah. So now this identity says 1 plus cotangent squared theta is equal to cosecant squared. Or you can write it like, sometimes it might be better just to write it 1 plus cotangent theta is equal to 1 divided by sine theta. Because when we do derivatives, things like these kind of pop out, and you're just like, oh, yeah, I remember. All right, sweet. And then I guess the other thing that's kind of important to know, since we're diving into cosecants and secants and cotangents. I think cotangent's going to be the easiest because like tangent's opposite over adjacent, cotangent is just adjacent over opposite. And when we use sines and cosines, like hell yeah, that's just going to be a percentage. Like anytime you take the hypotenuse times the sine of an angle, like this from engineering comes up so much. It's just the percentage of the hypotenuse in this kind of cardinal direction, or orthogonal direction, I should say. And this comes up quite a bit. You always use like the hypotenuse times that percentage in that direction to get that component, and cosine is going to be this component. What is sine of an angle? I mean, we know what the angle is, you know, and when we take the sine component of it, well, you know, if you take the larger number, the hypotenuse, times the sine of the angle, times that percentage, you get this component. So h sine of the angle is going to give me, in this case, oh, this is wigging me out. Oh man, I feel like this is just like an identity, but h, like 1 sine theta gives me sine theta in this case. Oh, that is holy Toledo. I'm wigging out. Okay, so if we have the angle, the sine of the angle is the opposite sine theta divided by the hypotenuse. Yeah, I guess I just I don't play around with this kind of unit triangle enough, but hell yeah, that's going to be the definition of sine theta. It's going to be this, and it's just, yeah, that's messing with me, because this sine of this angle, typically I kind of think of it as a percentage, but in this case, for this triangle, this is the distance. If this is 1 meter, this is sine theta in units of meters. This is cosine theta in units of meters, and the ratio in meters divided by meters. So this sine theta is still the ratio of this divided by the hypotenuse. Whew, that was brutal, because what I wanted to get to was cosecant theta. All cosecant theta is just 1 divided by sine theta. And so, hell yeah. So if the angle is what it is, and you take the sine of an angle, cool, this gives you the ratio, you know. And that's the ratio opposite over hypotenuse. 1 divided by that ratio is just that ratio flipped. So we're going to get, instead of opposite divided by hypotenuse, you know, get into the habit of saying hypotenuse divided by opposite. Sweet. So now cosecant is now just the hypotenuse divided by the opposite. But in this case, that's where, like, I kind of like sines and cosines, because sine and cosine is just, it's percentages of the hypotenuse. If this hypotenuse is 100, and you can see, hey, this maybe looks like 50 to 60, sweet, it's like 50 to 60%. It's going to be 0.5 or 0.6 times whatever that hypotenuse is. And sine and cosine will always be between 0 and 1. You know, in two-dimensional directions, just geometry, when you're getting absolute values, well, sure, it's also going to be between -1 and 1. You know, it's going to oscillate like a sine wave. Cosine's the same thing. But when you flip that ratio, you know what I mean? So if I have a ratio that could be either 1, I could have it be 0 divided by 1 or 1 divided by 1. When we flip this ratio, you're going to get 1 divided by 0, and that's going to be infinity. And you're going to get 1 divided by 1. That still stays as 1, but now when you have the opposite of it, when you have 0 divided by -1, I mean, yeah, so cosecants and cosecants and secants are this ratio flipped. Secant is the hypotenuse divided by the adjacent. We're focusing on cosecant today. That's going to be, the ratio there is the hypotenuse divided by this side. So it can be positive to negative infinity. And I'm not going to go over it, but don't let that confuse you, the negative infinity to positive infinity, because, like, just think, like, what are you, let's say you're dealing with angles of, like, 89 degrees to 1 degree to 89 degrees, you know what I mean? Just don't go to the extremes of 0 degrees and 90, and, your ratio is going to be no more than 1 divided by 60 or 60 divided by 1. You know what I mean? So kind of keep that in mind. Oh, and that's probably not true. That happens for tangent. I don't know if that happens for cosecant. I would have to, at a 1 degree angle, man, what are you going to get? I honestly don't know. I could figure it out, though, because you have small angle at 30 degrees. That's going to be 0.5 radians. And if your radius is like 1 meter, you're going to have this distance to be 0.5 at 30 degrees. And so at 1 degree, you're going to have 0.5 divided by 30. So you're going to have 0.016, and you're going to have the inverse of that. Yeah, so yeah, same thing. So I was right. You're going to have a ratio of 1 over 60 or 60 over 1, just depending. So that's pretty cool. Alright, hell yeah, I just had to graph cosecant just to make sure. And so now we're set. Now we can start diving into the derivative. But I hate this, because you're just like, well, what is the derivative? Well, who knows? And let's minus the derivative. What is the cosecant of the ratio? That's the other thing. With right triangles, like one rule that I kind of follow is you only need to know 2 things. If I know this angle and any side, the hypotenuse or just one of these sides, I know everything about this right triangle, because we know the ratios between those things. And if I don't know the angle, but I know 2 sides, like, typically you'll know like this side, A and B, and using the tangent, ratio of the tangent, you know that if the ratio between A divided by B is a ratio, maybe it's like 2, and what would that mean? That means that A is twice and then B is just once. So look at that. You get an angle, like that ratio can only be one triangle, and that triangle's maybe like 57 degrees or something. Who knows? We could look it up. Inverse tangent of 2. And I need to be in degrees. Alright, yeah, 63 degrees. Alright, sweet. So yeah, keep that in mind. Yeah, you just need to know 2 things about a triangle. Where were we? Alright, yeah, we were trying to figure out what does this cosecant mean. It's like the arc cosecant. The arc, tangent, arc cosine, arc cosecant of an angle. It means that if I identify this ratio, so let's just pick one. We said it could be between 1/60th to 60. Let's choose a ratio of 2 again. You know what I mean? And just see even what that means. If I have a ratio of cosecant of 2, well, let's write cosecant and know that cosecant is related to, so we're going to say cosecant of that ratio is equal to 1 divided by sine of that ratio. And my brother was saying, hell yeah, if you know that like cosine of an angle, well, that's going to be related to secant of that angle. This has a C right there and an S right there, and this has the opposite of that. If you do the same thing, sin, well, you don't have the same letters, and then cosecant, you have 2 of the same. So this one's just kind of the oddball, but secant, I think visually you can be like, oh yeah, just like say it backwards, cosine. Alright, and then say cosine backwards, secant. Alright, sweet. So I think we have that. Okay, so if sine of the angle, you know what I mean? That means that if we have, and I'm sorry I'm writing it like x, I did not want to start doing that. You know what I mean? I want to make sure that this is an angle where x is going to be the ratio. So for this video, anywhere where you see x, that's going to be the ratio. Anywhere where you see theta, that's going to be the angle. Sorry, I kind of lost that convention. But if I have sine of the angle, cool. What does this mean? It means that I have a triangle that has an angle, you know what I mean, that I know, like I know this number. And because I know this angle, I know the ratio of all these sides, you know. I don't know the length of any of the sides, but if I know the angle, I know the ratio of every side. As long as I know this angle and I know it's a right triangle. Cool. You know what I mean? So that's the fact that you know it's a 90-degree triangle, that does give you that extra piece of information. But just in general, if you know two things about the triangle, you know everything. If you know the angle, you know every single ratio about it. What this is going to say is if I know the angle, I'm interested in the sine of the angle, which is the ratio of this opposite over hypotenuse. Cool. So in this case, this might be like 2, this might be 3, and the ratio is going to be 2 divided by 3, or 0.6. You know, 0.6. And so what would be the cosecant of this angle? Well, it means that I know the angle. Cool. But I want the ratio of the hypotenuse divided by the opposite. That's going to be hypotenuse divided by the opposite, and that's going to be 3 divided by 2. So this ratio is going to be 1.5. All right, hell yeah. So we're getting closer to understanding even what the hell the cosecant is. It's a ratio. So now mentally I can be like cosecant. It's a ratio. It's related to sine as the inverse, you know what I mean? So when I see cosecant, I'm thinking sine. I know that it's like opposite over hypotenuse, but this is the ratio. When I see inverse cosecant, I know that this is the ratio, and I'm going to say it's the hypotenuse divided by the opposite. Alright, so hell yeah. So at least I know that part. And if I know this ratio, the hypotenuse divided by the opposite, I don't know if you call this like the anyway, let's not sound like the Matrix, but if we take the cosecant of this ratio, or it's basically saying if I have that ratio, hey, I should be able to, in my calculator, hit a button and out pops the angle. So that was just a long way around saying if you ever see this inverse cosine, which it's not 1 divided by the cosecant, inverse cosecant, these with a ratio generate an angle. Alright, booyah. So we're getting closer. And so what we can say, so that's why I don't like these derivatives, because they're not equal to anything. And it's just, it seems necessary to be like, well, the angle is going to be, the angle that we're trying to find, the angle on this side, is going to be the inverse cosecant of the ratio x. Hell yeah. And let's even spell this out. So we have the angle is the inverse cosecant of the ratio. And in this case, the ratio is the hypotenuse divided by the opposite. And because the hypotenuse is the bigger number, and the opposite could be anything between 0 and 1 as a percentage. Holy Toledo. This thing could be infinity to negative infinity. In a two-dimensional space, this could be 0 to infinity. But we know that sine and cosines also go into the negative realm. Alright. Alright, sweet. So, booyah. So now we're going to tackle this problem. And like I said, I've never tackled it. And so that was kind of just the intro to like that. That's knowledge you need to know going in. And this unit triangle is really important. So let's bust that out again. We're going to have sine theta cosine theta 1. So let's bust out all the ratios. Let's say, and this is our angle. Alright, what is sine theta? That's going to be opposite over hypotenuse. So that's going to be sine theta divided by 1. What's cosine theta? Adjacent divided by hypotenuse. So that's going to be cosine theta divided by 1. Alright, we're on a roll. Tangent, opposite, divided by adjacent. So that's sine theta divided by cosine theta. These were just bizarre ones because they just seemed like identities. But write them like a fraction, and then you can see that, hey, I'm including the ratio. All right, now we're going to do 1 divided by sine theta, which is also called cosecant of the angle. And that's just going to be this flipped, 1 divided by sine theta. Then we're going to do 1 divided by cosine of the angle. That's going to be secant theta. And that's going to be 1 divided by cosine theta. It's the hypotenuse divided by sine, and in this case, hypotenuse divided by cosine. All right, and now we're going to do cotangent of the angle. And, well, I guess that's 1 divided by tangent of the angle. And it's just this flipped. So it's cosine theta divided by sine theta. All right, hell yeah. So just using this unit triangle, I think at this level, you at least need to do this, and just don't forget about Pythagorean's theorem. Because why? Because sine, like a squared plus b squared is equal to c squared, so we have sine squared theta plus cosine squared theta is equal to 1. And just know that we can divide all these sides by sine squared. And that's kind of interesting. It's like, I'm sure there's a more logical way to get to those identities, even just by using this unit triangle. Because if I see that, yeah, because, hey, if secant theta is 1 divided by cosine, well, check it out. So I could bring cosine upstairs and secant down. So cosine theta is 1 divided by of secant theta. Hell yeah. So right here I could put 1 divided by secant theta, and right here the same thing. Sine theta is 1 divided by cosecant theta. And I'm answering my question. You know what I mean? This is going to be 1 divided by cosecant theta. This is side A, this is side B. And guess what? These are synonymous. These are equal. These are equal. Hypotenuse hasn't changed. And so now we have this ratio that says 1 divided by cosecant theta squared plus 1 divided by secant theta squared. Well, guess what? That's the hypotenuse. So just don't forget about Pythagorean's theorem. And obviously you can square the 1 just stays the same, and then the square comes downstairs. Secant squared theta plus, anyway, I think we got it. And yeah. That doesn't give us those identities. Like obviously if we have this and we can divide by, you know, you do it 2 ways. You take this and divide by, let's do it. You divide by sine theta on both of them, and then you're going to get 1 plus cotangent squared theta. So we're going to get 1 plus cotangent squared theta is equal to 1 divided by sine squared. And I like to write it like that, 1 divided by sine squared theta, because sometimes you might have to. And then divide by cosine, you know, divide by cosine here, that's 1. And then you're going to have 1 divided by cosine squared theta is equal to 1 plus, this is going to be tangent plus 1. So you're going to have tangent squared theta plus 1 is equal to 1 divided by cosine. Or you could just say this is cosecant squared. All right, hell yeah. So that's the that's what we have there. All right, booyah. And, you know, and then for these problems also is don't forget, because this will come up a lot. I mean, you might as well go over these first instead of being like, you know, pulling them out of a hat like a magic trick. Because if I have this, if I have sine squared theta plus cosine squared theta is equal to 1, can't I just solve for cosine? Because I had to do that doing the inverse sine of secant. I mean, inverse sine of a ratio. Doing the arc sine of a ratio, or inverse sine, I used this. So I needed to find, so how do I find cosine, just cosine of the angle? That's all I want to do. So I'm going to take this to the other side, 1 minus sine squared theta, and then I'm going to take the square root of it. All right, hell yeah. So we can do that with any of these. I can find cotangent just by taking this, like subtracting a 1 and then taking the square root of this. Sorry, and that would be cotangent. All right, sweet. So there's just a lot of different things you can do there. Okay, so we probably don't have enough space to do this. I'm probably going to do another printout. But the general setup for these is hella, get this as an equation of the angle. The angle you're trying to find is because you know the ratio, and this -1 means like arc sine or inverse. It's an inverse ratio function, inverse sine function of this ratio. And we're just calling that ratio just a number, just a value x. And we want to take the change, derivative of the angle with respect to the ratio. So we're taking derivative of the angle with respect to the ratio. So dx. And this is where this also can be nonsensical. Because like, when would you use this in the real world? Well, you might have something of like, hey, I know the angle is going to be a function of the ratio, and it's going to be cosecant of x, and I want to find, and so it's a rotational problem. And if I take the derivative of this, I would typically take the derivative with respect to time. The change in the angle with respect to time is omega. That's going to be in radians per second. But I can't take the derivative of this side with respect to time because I have an x right there. So this is where I would have to use the chain rule. I could take the derivative of this with respect to x. Cool. So we have inverse. I'm sorry I'm calling this cosine, but bear with me. And I would take the derivative of this with respect to x, but I have to use the chain rule. I also have to do dx d theta. No, I'm sorry, dx dt. Holy Toledo. Derivative with respect to time. I can't. I'm going to take the derivative with respect to that value x and then dx dt. And again, I'm horribly sorry for... No, this is good because this is the ratio. I'm confusing myself because I definitely want to use that standard where if I have x, that's going to be the ratio, and if I have an angle, that's going to be theta, just not to confuse. In some problems, like you're not going to, like a lot of math people that solve these, they're not going to use the angle theta. They're going to call the angle theta y. And man, that's a bummer because I don't think it visually means anything at that point anymore. People do that with logarithms all the time. You're just using y and x. And I don't know, I guess it's consistent, but it kind of loses the meaning. All right, so this is why you would take the derivative with respect to x. So that's what we're going to do today, is we're going to do that, but we're going to do the cosecant. Sorry for writing cosine there. So we're going to take the inverse cosine of x, and we're going to take the derivative with respect to x. Kind of a meaningless thing, because all we're saying is that, hey, we're going to change this ratio. Maybe the ratio was 2. And, we forgot to do that. So if this ratio is 2, the hypotenuse, this part is 2. And then the opposite is 1, because the ratio is 2 divided by 1. That's also kind of cool to get into the hang of. And then, I don't know, I would just start dotting one of the dimensions, and then try to go the other way by 1, and just make sure you're still ending with a right triangle. So if I came in here, 1's right here, hell yeah, so that's pretty good. So here's the opposite. It's a side of 1. The hypotenuse has a side of 2. And that is the representative triangle that represents 2, 1. Cool. And so when I take the inverse, when I take the cosecant, the arc cosecant or the inverse cosecant, man, I need to come up with other ways to say that, of this ratio, 2 over 1, the hypotenuse over the opposite, this is the angle that I would, so it's going to be, and I wouldn't do that. I would say this is the inverse sine on my calculator. I don't have an inverse cosine button. Inverse sine of 1/2, 0.5. Yeah, this is a 30-degree triangle. All right, booyah. So now what this means, what this says, the derivative, because every time I said I wasn't going to do a derivative until you at least explain the changing of the derivative with changing this value of x. All right, sweet. And again, the change in this is the angle. This whole thing is the angle. And so what we're saying is we're going to change the angle. So it's change in angle. Man, like just the fact that I don't write this every time. This is a good habit. Anytime you're doing the derivative, sure, you're taking a derivative of the function, and maybe this is like, how many apple pies, it's an equation for making apple pie. Like I thought that would be like a good one where it's like, hey, if I have 8 apples on the table, maybe that's enough to make 1 apple pie. You know what I mean? And then you could you could do that. But anyway, that's the other thing in math and physics. It's just like, it gets so complicated. You're just like, what does this even mean, or what are we even using it for? I mean, at least we know that this is an angle, and so we're going to take the derivative of it, which is changing the top divided by the change in the bottom. Cool, and that's it. Sure, the change in the bottom has an incremental change. Cool. I mean, just like when you get an equation for acceleration, no one says, hey, I'm going, I'm falling at a speed of 7.5, or I'm falling at a speed of 6.6 meters per second per 1.5 seconds. And that's not even right. I got to go the other way. But you know what I mean? Your units are always, I'm falling at a speed of 10 meters per second. I'm changing my velocity in 1 second. So the bottom will always be an incremental change. But let's see how this works out. But when you're just finding the value for the derivative at any given point, you're just trying to find a change in an angle. Doesn't matter if it's incremental, and you're trying to find a change in that bottom part. And in this case, the top part is an equation for angle, and the bottom part is that ratio. So let's change the bottom part. We're going to change the ratio to 3 divided by 1. So let's do that. The hypotenuse would be 3. Because look at this. We even know where to go. The ratio of cosecant, now we're just so pro, we're just like, hell yeah, that's going to be the hypotenuse divided by the opposite. And sometimes it's hard to get these where you got a right triangle. And so hell yeah, that's going to be 1. And then so we have 1, and we have a ratio of 3. So that looks like a 22-degree triangle. You know what I mean? So let's see if that's right. Inverse sine of 1/3. All right, that was a pretty good guess. 19.5. Okay, hell yeah. So now we have a change in angle of, about 10. So we have about a 10-degree change in angle, and we change the ratio by 1. Cool. So now this is sweet, except the only thing when you're dealing with sines and cosines, you better be using radians, because not getting into that. But just know that a 30-degree triangle, I need to make a separate video on why we don't use diameters. You know what I mean? Hell yeah. This is why we use radians, because if you have a radius of a circle and you cut a string, alright, hell yeah. Yeah, if you cut a string to the length of this radius and then start draping around the circle, hell yeah, you get that far. And that's what we call 1 degree in radians. But it's just kind of cool because it works out. Well, oh man, I need to almost prove why it works out. But, oh man. So, yeah, this arc length is, if this radius is 1 meter, 1 radian, you would get 1 meter. Now, if it was diameters, sure. If you took the diameter, you would get all the way to here, and then we'd call that an angle of 1 diameter. And then the diameter times 1 diameter would get you this arc length. So that would also make sense. But when it comes to the small angle, like when you get down to, if this is 1 radian and it's approximately 60 degrees, and you get an angle of, and this radian is, I don't know if that's the, But anyway, when you get to a 30-degree angle, so 30 degrees, this length will be like 0.5, because the radians is 0.5, and then this length is 0.5. But with diameters, this diameter of this, it wouldn't be 0.5. This would be a 0.25 diameter degrees. You know what I mean? Because this, all the way out to here, is 1 diameter. So right here is 0.5 diameters. But guess what? If this is a 1 meter radius circle, this distance is approximately 1 meter. and then the diameters is 0.5 diameters. So that in a nut, I need to be able to explain that just a lot faster. But it was worthwhile. I didn't even want to touch that, but I think that could be if I was able to make viral videos, which I'm not. That would be a good one. Be like, why don't we use diameters? You could have angles and diameters, but the small angle theorem, it just wouldn't be useful. I mean, you would get an angle of 0.25, and then you just have to multiply it by 2 to get this length, to get the opposite or the arc length. Hell yeah. So that's why we use radians. So this kind of special thing about radians. And booyah, if we have a 30-degree triangle, we have 0.5 radians, it's like 0.523. What are we doing? So then that means that if we have a 10-degree triangle, well, we have 1/3 times 0.5. I know it's kind of messy, but 1 divided by 3 times 0.5, hell yeah. So we have 1.6 repeat radians. And what were we doing? We're taking the derivative of this angle when we change the ratio. So we changed, and we could have done it the opposite. We could have just changed the angle and saw what the ratio changed, but we chose to just change the ratio from 2 to 3. Angle changes from 20 to 30. So, and then the derivative is the change in the angle divided by the change in the ratio. And like I said, kind of a meaningless unit, but once you use it with the chain rule and you multiply by then it actually evens out, where you take this answer for the derivative, multiply it by what would that be? That would be the dx dt. Oh yeah, the change in this ratio with respect to time. Yeah, maybe you don't know the change in the angle with anyway. So yeah, chain rule is your friend, but you need to get a number for this. So in this case, we're going to have a change in angle of 0.166, and our ratio changed by 1. So hell yeah, this is the number for the derivative at somewhere in between an angle of the derivative of x, somewhere in between a ratio of 2 and 3. If we throw in 2 here or 3 here, hell yeah, we're going to get a derivative of this of about 0.166, so hell yeah. Wow, that was brutal. All right, let's print off some more of these and then start see if we can actually do this from scratch. All right, hell yeah. So we're back, and sweet. So now we can just do it. We can say that this equation is equal to the angle. So I'm going to say the angle we're trying to find is taking this inverse of the ratio x, the cosecant, inverse cosecant, arc cosecant. Okay, hell yeah. And now we're going to take the derivative of this with respect to x, and we've kind of gone over why we do that. Because maybe you want to take the derivative of this with respect to time, you got to use chain rule, but we're just going to do that first part. Oh, sorry. All right, so now what? Well, this is ugly as hell, so we're going to take this side of the equation, because if you're taking the derivative of both sides, it doesn't matter. Yeah, that was kind of a fascinating thing for me. It doesn't matter where things are located. So we're going to go back to the angle is cosecant of the ratio. So we can, you can take the cosecant, you can take the cosecant of both sides. Or, I don't know. I just like, hey, get this the hell over there. So we're going to say the cosecant of the angle is the ratio. We kind of talked about that. If I know what the angle of this triangle is, and I want to know the cosecant of the angle, that's the ratio. That's going to be hypotenuse over opposite. So hell yeah. Now I can take the derivative. We're going to leave that because this is an equation we want to come back to. The fact that x is equal to cosecant theta, always in these derivations, you're going to use that. So let's just rewrite it twice, because we want to take the derivative of this with respect to theta. So we have cosecant of the angle, derivative of, holy hell, what are we doing? You know what I mean? Sorry about that. No, we have cosecant of this angle, but we want to take the derivative of this with respect to that ratio. You know what I mean? So keep that in mind. And but we can't, so we'll have to use chain rule here. But we'll do the derivative of this function x with respect to x. Oh, finally, you know, for the love of God, this is an easy one. It's just 1. Okay, but all right, hell yeah. So the chain rule says that I have an angle here and I need to take the derivative with respect to the ratio. I don't have the ratio here. So we use the chain rule, which says, hey, the derivative of what we're trying to figure out is the derivative of theta, because it has a theta in it, and then d theta dx. Cool. And then the foreshadow is all along we're trying to find d theta dx. Cool, this is like the derivative of the angle, the change in the angle with respect to x. It's not the change in the angle with respect to time. You know, you'd have to do, you know, you would use this in a legit problem. You know what I mean? Just as is, this is just one component of that legit problem. But cool, but you still need to know what this is. Anyway, hell yeah, when you take the chain rule of this, you have the derivative of this function with respect to theta, and then d theta dx. And cool, d theta dx is what we're trying to find. You know what I mean? So set this, you know, equal to everything else, and then we're just good. But then you have to get things in terms of x. We don't want anything in terms of theta. So that's why, you know, some of these are just like 1 divided by the square root of u, and then 1 minus u squared. Anyway, and we'll get there. Okay, sweet. So we can't take this derivative with respect to x, but we can do d cosecant of the angle with respect to the angle. We can take that derivative, but then we use the chain rule to say d theta dx, and then this is all equal to 1. All right, so now we're good to go. This is going to be our solution. We just need to figure out what the derivative of cosecant is. So let's come over here as a separate problem and try to do that. I do know that cosecant is 1 divided by sine, so we're going to take the derivative with respect to theta of 1 divided by sine theta. All right, sweet. And then I am now not ever going to use, well, I don't know ever, but I would say stay away from the quotient rule. You don't need it. Well, I don't know. We should do these 2 ways, because with trigonometry, maybe one way is the easier way. We'll do it the quotient rule first. So we're taking the derivative of this with respect to theta. The quotient rule says bottom d top. So that's sine theta, derivative of 1 is 0. Cool. Minus top 1. D bottom, so that's just going to be 1 times cosine theta, all divided by the bottom squared. Actually, yeah, it's probably pretty slick to do it that way. So what does this simplify to? This simplifies to, well, negative 1 cosine theta divided by sine squared theta. I've been doing my negative 1s in brackets just so I know that it's you know, I just don't lose it, and so I'm happy about that. Cool. So now we have this. And how would we have done it otherwise? Well, you do this. You say that 1 divided by sine theta is the same thing as sine theta to the negative 1. And we're going to take the derivative of this. How do you do that? You set it up like a u substitution. You know, derivative of anything to a power. You know what I mean? Or just wing it, you know, and it's kind of a fun way to learn it. Bring down the power, so we got negative 1. We're going to take this sine theta to the power, drop the power by 1, so this is negative 2. And then you guys still got to take the derivative of the inside, so that's going to be cosine theta. And look, we get the same exact thing. This negative 1, cosine theta on top, sine theta, sine squared theta below. Hell yeah. So whatever, I think this can make less mistakes when doing monsters of, if you're just doing if you're differentiating for days, this keeps everything upstairs, and I think for me I can make less mistakes. Alright, booyah. So we did it. And so now we just, let's write it over here just to see. Because yeah, now you kind of have to do the game where you're just like, I don't know, how do we convert all this stuff? And I think you just have to do a few of these to be like, oh, okay, well maybe, but we have to use this property that x is cosecant theta. So if we have a cosecant here, which is 1 divided by sine theta, cool, that's going to equal x. But guess what? X squared would be cosecant squared. Or x squared is going to be 1 divided by sine squared theta. Oh, we have a sine squared theta. Hell yeah. So we have an x squared here. You know what I mean? So we do have that. This is an x squared. We can just put that in right now. But this is where it's just like, well, what do we do with this cosine? We need to get cosine in terms of, well, that's why I don't mess around with cosecants or secants. Just turn everything to sines and cos. Sometimes it's easier. And in this case, hell yeah. I know that cosecant is just 1 divided by sine. So how do we convert cosine to sine? Well, that's why I did all those ratios just right off all these identities right off the bat. I said if I have sine squared theta plus cosine squared theta is equal to 1, we could solve for cosine. I mean, do we want to do that one again? Probably not. But get sine squared over here, 1 minus sine squared, take the square root of it. So booyah. So I'm going to say cosine theta is the square root of 1 minus sine squared theta. Hell yeah. And yeah, I don't even know if that was helpful. That probably wasn't. Because how do I... Oh, no, I'm good. Maybe. I can just say that if this... Oh yeah, so this identity right here, well, I can just flip it. I can say 1 divided by x squared is sine squared theta. Hell yeah. So now I'm good to go. So with this... Oh, and then this is still equal to what we're trying to get. Cool. So let's keep it like this, and then just start adding. So I have the negative 1. We'll do the cosine. We'll do this part first. Cosine theta is equal to square root of 1 minus sine squared theta. And so that's going to be equal to the square root of 1 minus 1 divided by x squared. Cool. Alright, so I think we're... And this, like I said, this is the first time I've ever done this. I mean, I can't say that... I did glance. I mean, I did see that cosecant is... so I can't say that I didn't look at this. But I just don't know how to get from here to there. But I've done the other ones. But it does have an extra term. And so I was just kind of aware of that. But I didn't go into this problem with no knowledge. Yeah, this is kind of fascinating. Because people that make these videos on YouTube, they're just like spitting out textbook answers. And it's like cool, but it's kind of just a memorization scheme. Like you really want to forget how to do it. And then that's what I do. I do videos from that perspective. Alright, sweet. So that was the cosine part. We have a 1 divided by sine squared theta. Oh, sweet. So we have an x squared. So we're going to take this and then just multiply it by x squared. Hopefully I didn't mess that up. But no, we're good. So we have x squared. And then we have what we're trying to find, the d theta dx. And then this is equal to 1. Alright, so we just have to get everything over here. So we're going to say d theta dx is equal to, and to get this stuff over here, we got to divide the hell out of it. So, I'm sorry, I'm just going to write it right here. D theta dx is going to be this 1. Now, when we divide by negative 1, That's the only thing that just mentally, I just know that I can just take the negative to the other side. Sure, you're going to divide by -1 over here, -1 here, but it's the same thing as multiplying by -1. All right, so sweet. So we're going to have that -1, and then everything else gets divided. So we're going to have -1, and then divided by x squared square root 1 minus 1 divided by x squared. And I hope I made a mistake. You know what I mean? Because maybe I did. You know, maybe this isn't the simplest way to write this. So derivative of cosecant, they say that it's, yeah, because I feel like I made a mistake maybe. But 1 divided by x square root of x squared minus 1. So that's what they got. We got 1 minus 1 divided by x squared. Yeah, that's kind of a bummer. So, oh, and they actually got a positive value for that. So that is interesting. And you know what? I think my way jives. This 1 divided by x squared. And let's, man, I need to, let's store, what, 25 stored as x? And we're going to do this one. 1 divided by x square root x squared minus 1. All right, booyah. And so that gives us that answer. Now we're going to come here. We're going to do -1. Well, there's no way this is going to be, yeah, I don't know. I think we're just messing up. Yeah, I don't know where that -1 changes. My bad. Especially if we have a square root here, this is for sure going to be a negative number. It can't be anything other. But let's see if it even is a real number. So we're going to have x squared square root of 1 minus 1 divided by x squared. All right, we get the same number. It's just negative. So I think I messed up on. Well, let's go back. Bottom d top, is that the quotient rule? Bottom d top minus top d bottom, all divided by the bottom squared. Yeah, so we should have a negative here. And that's going to be the derivative of this. And so we'll have a negative cosine divided by sine. All right. And, oh, if we have a negative cosine, yeah, this is kind of fun. All right, hell yeah. Sorry about that. Camera cut out, but we're back. And, yeah, so it's fascinating that I got the right answer. It's just the sign change. But I think we did everything right. I mean, setting it up, we're taking the derivative of cosecant is equal to 1. Cosecant, just to make sure, is 1 divided by sine. Taking the derivative of that. Low d high minus high d low. And this is, derivative of cosine goes to negative sine, but this just stays the same. So, yeah, so we do have this. But I was thinking, sure, we have a -1 minus cosine. So let's go back to this equation and say, hey, let's get negative cosine over here. And that's going to be sine squared theta is -1 is equal to negative cosine squared theta. Oh, bummer. No, I don't want to do that at all. Ah, holy hell. So, anyway. No, we were good here. Oh, is this minus tripping me up? Yeah, now I'm just trying to find my errors. So, I think I was okay with doing this. This cosine of the angle is the square root of 1 minus sine squared theta. So we have 1 minus sine squared theta. Cool. And, yeah, this is a bummer. Because I thought we were doing pretty good. I mean, we did really good. I just don't know where this negative goes away. Alright, so this 1 over sine theta squared. Yeah, so that's going to be x squared. Cool. So that's that x squared. Yeah, and then we just have this -1 cosine theta. I don't know. You know, I mean, maybe there's something cool that I'm not aware of. Yep. All right. So let's pretend like we just made a mistake. So we have -1, and then we have this. Huh. Yeah, that's interesting. Alright, I don't know why I'm tripping out. I do this all the time. I just kind of read the wrong thing. No, there is a negative there. So yeah, so this negative does stay. And so the answer has a negative. Sorry about that. So the answer is -1. Yeah, we basically got the right answer. But they just simplified it to x is equal to the x squared minus 1. Where we got this. We got 1 minus the square root of x squared. So let's take a fundamental look, because if we do have this, you know, so this comes up a lot where you're just like, okay, I have a square root. You might think like, okay, I have a square root here. I do not know what that means. But we have to go back to Pythagorean's theorem. We have a squared plus b squared is equal to c squared. We're dealing with right triangles, you know what I mean? So we can do 3 different things. We can say that, sure, this hypotenuse is a squared plus b squared, square root that. And then these sides, I'm just going to do b first. I typically do that. We're going to say, is the hypotenuse squared minus the other side squared? Cool. So that is going to give us this other side of the triangle. And then the same thing for a. You take the hypotenuse squared, it's the larger number, subtract it by the other side squared, square root that, and you get that side. So when I see this, I know that I have a triangle where the hypotenuse is x, and then one of the sides is 1. And then I want to know what the other side is. Sweet. So let's do that. So I mean, yeah, that's totally this squared plus this squared. Or I mean, yeah, this is the scenario where the x is your hypotenuse, so we have c squared. You have to subtract it from one of the other sides because we're trying to, this whole thing represents the other side of the triangle. Okay, sweet. So now let's just, what do? Oh, and didn't I say that if we know 2 things about a right triangle, we know everything? So I can solve for this side just by using my equation. Well, that's going to be that. It's going to be the square root of x squared minus 1. I don't know if that really helps us. And we're saying this is 1, so we'd square 1, but it's just still just 1. Man, that's a bummer. Yeah, so this is that other side. What else? And okay, so and in the one that we got, we said this triangle was going to be 1 was the hypotenuse. Oh, this is sweet. This is cool because hey, x might be a number that's greater than 1. So how do we turn this triangle into a unit triangle? Well, to do that, you would say that I want to take this side, and we know that this side is a percentage of this hypotenuse. So this is cool. What I do is I take this side and then divide it by x. Okay? And then because if I take this side, and let's do this. This is kind of fascinating. If I have a 30-degree triangle, or maybe we should do let's do a 30-degree. I always like to do that. We have, and I'm just going to make this side 10. That means that this side is 5, and this side is 8.66. Cool. Now, if I wanted to make a unit triangle, I would take this side, 5, divided by the hypotenuse, and I would take this side, 8.66, divided by the hypotenuse. That gives me a unit triangle of 1, 0.5, and 0.866. Cool. So just right here is like they're not using a unit triangle. I am. I'm using a unit triangle. That's how I got my answer. But oh, yeah, no duh. So, yeah, I totally forget about this mathematical property. So, no, let's continue what we're doing, but I see what they're doing. They're just multiplying both sides of the equation by, or maybe, if you multiply both sides of the equation by the same, anyway, maybe not. Okay, so to get this in terms of a unit triangle, we're going to do 1 divided by x, and that's going to be this divided by x. Man, and that's going to give us a triangle of 1. So if we know that, then we know that this side is going to be 1 squared minus 1 divided by x squared, square root that. And that's exactly what we got. We got 1 minus 1 divided by x squared, square root that. So we're still getting, we're still getting this side. Yep. Huh. Oh, I didn't even notice this. That I have an x squared out here and they just have an x. So yeah, for sure, we can totally simplify this. So, yeah, this is interesting. Yeah, so let's do that process of simplifying our answer so we still have this -1. And I'm looking forward to it, you know what I mean? I think I have the math skills to see how they got from here to here. That's kind of the fascinating thing about learning is like it can be impossible to go from one step to the other step and you have no idea how they did it. So we're going to do 1 minus 1 divided by x squared. Okay, sweet. So how do we get this inside the square root? Well, one way to do it is just do this. We're going to take x squared, we're going to square it, and then take the square root of it. That's the same thing. We squared it, took the square root of it. So that's the same thing as the square root of x to the 4th. Hell yeah. And yeah, now this is going to go real slick. Now, if I really cared about this problem of doing it just by myself, yeah, I would just say, hey, let's not look at anything. Well, no, we had to look at we had to look at the form that they got it. Definitely checking my error on the negative, but still, this is still pretty sweet. We still need to get the form that they do, and because I would have just stopped at the form that I got it. I would just say, hell yeah, I'm done. And this is good enough for me. Like, this should be written in a book because this is the form that you would first get to. Cool. All right, so now that we have this in the square root, we're going to have -1 square root of x to the 4th square root of 1 minus 1x squared. So anytime that you get this, hell yeah, now you can just take the square root of both of them. So this becomes -1. The square root of everything, we have x to the 4th, and it's just times 1 x squared. All right, booyah. So now you kind of see the process is unfolding. -1 square root. This becomes x to the 4th, and then this becomes yeah, well, I guess we got more steps. So we have x to the 4th minus x to the 4th divided by x squared is just x squared. All right, sweet. So now we have it like that. And now how do we simplify this? Well, let's factor out an x squared. I'm sure you could have gotten here a little bit faster, maybe not though. So we're going to say, hey, we have an x squared. Factor that out. So now we have x squared minus 1. Booyah. And we're going to take the square root of that. All right, hell yeah. And, yep, so taking my time, this is the same thing as the square root of x squared, the square root of x squared minus 1. Now, this is stuff I will always do now because, like, little steps like this, how to get something in the square root, like having just a foolproof process to do that is just real important because you don't want to be, like, just scratching your head to figure out how to do that, especially when it comes to test time and stuff. I mean, not even test time. It's just an enjoyable process, especially for me. So we got this outside, and we see that x squared Square root that is just x, and booyah. So we have x times the square root of x squared minus 1. And this whole process, what were we even trying to do? We were trying to simplify this. So now we have the derivative of that angle, which is the same thing as the derivative of cosecant of that ratio with respect to x. Sorry I put t there. With respect to x is -1 x. So now we have this x square root x squared minus 1. All right, hell yeah. And I think I could do that. I wouldn't want to do it, but I'd do it another time. You know what I mean? Because that's what you would do, like in a problem where you're just like, ah, shoot, I have to take the derivative of this. Well, just go through this process. Do it at least a couple more times before you just always look up the answer. But yeah, that's going to help your skills. Don't just do it once. When you actually in the real world come across this, you know, start in on the process, knowing that you have the skills. You know what I mean? Take this to the other side, get it like this. Knowing that at the end you're going to have to, anywhere you have a cosecant theta, which is 1 over sine squared theta, you're going to input x. And just know that x squared is going to be 1 over sine squared theta. Hell yeah. And so that was the process that gets us there pretty fast. And know that when you take the derivative, you can't take the derivative of this with respect to x. You got to take it with respect to theta and then multiply it by d theta dx. And booyah, that's exactly what you want. You know what I mean? So that's kind of the process in a nutshell. And just to double check our answer, just to make sure we're 100%, derivative of cosecant is -1 divided by x square root of x squared minus 1. All right, hell yeah. So really happy about this one. And thanks for joining me, and that's a video.